we are actually CSQ. Today we'll be talking about car hacking made Easel. So this will be a beginner's talk on how we actually built this Easel within a month's time. Right, so for today's contents, we'll be talking about the objectives, how we got started, how we built the prototype, the test bench, and how we actually hacked the prototype, and the next steps. Okay, so I'm Alina. This is my teammates, Pace and Chun Yong. We are from the Car Security Quarter. This is our Twitter handler. So we have a total of about 18 members and counting. So we are part of the wider cybersecurity community group called Division 0 in Singapore. And recently we had a partnership with ASRG, the Automotive Security Research Group, and we run the Singapore chapter. There's a meetup group online that you can find. Okay, the objectives. So, as everybody knows that, the cars in Singapore are actually very expensive. So the main purpose of starting the Car Security Quarter was to enable and facilitate learning on automotive cybersecurity. And, one of the main goals is to facilitate and promote automotive cybersecurity awareness. So we do so by organizing villages and conferences such as InfoSec in the city, as well as HITB, and to actually perform outreach activities. So we'd like to actually empower like-minded security enthusiasts by gaining hands-on experience. In order to do that, we actually built a working test bench to cover the automotive security testing and cyber physical testing itself. So you can see that we actually use real car parts for our Easel. And ultimately, we like to contribute to the automotive cybersecurity industry itself through research and community engagement. And ultimately, we would like to conduct proper responsibility disclosure to any respective vendors for any vulnerabilities found. So can I have a show of hands who here drives to work or who here owns a car? Okay, cool. So, in the next video, imagine if this happens to you while you're driving home. Okay, so we actually did a replay attack on our prototype car itself. These parts are actually achieved from that specific vehicle. We are driving normally about 20-30 kilometers per hour. So, as you can see, the speedometer and the RPM meter actually increases. But we are actually driving at normal speed. So at times you may see that the speedometer returns to normal speed, like 30 kilometers per hour, because the ECU, the actual ECU is also continuously sending the right speed, and we are also sending our spoofing packets in there. So, but in order to maintain like the spoofing, we actually had to send data faster than the actual ECU to actually achieve this. Yep, so you can see that 300 kilometers per hour is actually the maximum. Okay, so we will be going through all of this through building the prototype and getting started later. Alright, so this is how we got started.
Alright, so this is actually just a very simple overview of what we were looking at, all the guides that we were following through, and this was what we got. So these are different protocols that's in the car. And what we actually want to focus on today is the CAN bus itself. Right below the CAN bus, you can actually see there's a CAN-FD. So CAN-FD is just like an extension of CAN. CAN usually transmits at 8 bytes, whereas CAN-FD increases it. It allows for 64 bytes instead. Right, so how to access the CAN bus is using the OBD2 port. OBD2 port is like, think of it as like your USB. You just insert into the port, and then you'll be able to like read diagnostic messages out of it. And that's how the car mechanics in the different, in like any technician will be able to read any, like let's say got any errors in the car. That's how they actually read it. But the two main points that we want to point out to you today is the CAN high and the CAN low, pins. So that's pin 6 and pin 14. So actually over here, you'll be able to see it, like let's say if you come up close to our Easel, you'll be able to see that it's only like 2 wires that's connected to our, transceiver. So this is how like a CAN packet looks like. In the next slide, we'll show you like an example of how it looks like. In the more important parts here is actually the identifier, the CAN ID, which is a unique identifier. It represents the message priority, and also it shows it actually corresponds uniquely to the different car components. And the next part that's important is the data length code, which contains all the important data field. Right, so over here you can see an example. So SLCAN is the interface, because we connected the CAN transceiver from our computer over to the ECU. And then that's the CAN ID, and that's the data field. This, we actually mapped out the different car components from the particular car model that we were testing out on. So in red, we can actually see the fast CAN, which actually caters to like more of the important modules like the ECM, and the blue part is actually the low speed CAN, or we call it VCAN. So it's for slightly less important functions in the car. The purple, the instrument cluster module is in purple because it's like a gateway between the FCAN and the BCAN.
Okay, so now we'll be talking about how we actually built the prototype. So we identified the following essential parts to build a starter's test bench. One of the main important things is the electronic control unit, which is the ECU. It actually allows connection towards the instrument clusters, as you can see over here. For the instrument clusters, it actually displays the speed, the RPM, so it actually allows spoofing and replay attacks. We also have another part that we actually just purchased, the ignition key cylinder and the immobilizer itself. So it actually provides the starter ignition signal for the ECU. So in the future, we hope to just turn the key and be able to start the whole Easel through the key itself, so it'll be more realistic. And part of the analysis tools that we use is the Cannibal. It's a small piece of device over here which allows communication between USB to CAN. And the CAN transceiver actually provides the differential transmit capability and the receiver capability from the bus to the controller. So from Pace's last slide, you can see that it's the whole mapping of the diagram. This is the parts that we currently own right now. So the ECU, the ECM, the PCM, powertrain control module. The ECM is the engine control module. The instrument cluster, the reason why it's purple is because it acts as a gateway to allow both fast CAN and body CAN to actually communicate between each other. So the body CAN itself, it's for devices that are really slow, like door control, your less critical portions. So hence, it's actually easier for us to map out the whole thing, to visualize the whole part of the car itself. So we actually chose to build a test bench for various reasons. One of it, most importantly, is safety. Testing on a real car, like what we did earlier on, is actually quite dangerous because you have no certainty of what the results could be. So the results are unpredictable. And the cost of fighting an actual car is definitely expensive. And we actually triggered some errors when we actually did the replay attack. And then demonstration, the test bench actually allows us to better showcase our results for presentations. And it's easier for us to correlate the parts for the different CAN IDs to simulate an actual vehicle itself. So the final design was placed on an easel. It was actually a joke because Chun Yong actually got married recently, and then he loaned us this easel. It was used to put his wedding photo, but this is now our prototype display. And then our car parts are pretty old. It's actually cheaper for us to actually purchase these older car parts because we are actually a non-profit group. We fund ourselves. And it does not have connected car vehicle features, but it's actually essential for members to understand CAN bus functionality. And then previously, we set up all the instrument clusters on the table itself, which is a hassle. We took about 1 to 2 hours to dismember all the wires and plug it back in the breadboard, as you can see there. And most of the time, we actually fry wires. We broke many wires, and it's not efficient for us to actually put it on just the table itself. So we decided to mount everything up for testing purposes and showcase presentation purposes. So now we'll show you how we actually hacked the prototype.
Okay. Hello. Yes. Is it working? Hello?
Sorry, the mic.
Test. Okay. Yeah, so Alina already just mentioned about some of the component. Maybe I should have put it in my back. Okay. Alina talked about some of the components that we actually pieced together and the reason why we put up on the Easel. So now it's about how we can actually make use of the setup itself to actually figure out how the car works. So with that, we had to have a systematic way of actually dealing with it instead of just poking around randomly. So the first thing we did was actually look at what are the CAN messages that are being done by an actual vehicle. And then after that, we try to replay these messages on the test bench itself to see whether we can figure out what each of these messages actually mean. In order to figure out whether there's other functionality also based on all these things, we also try to do some fuzzing. So we look at the packet itself, we try to spoof or create our own packets to be able to find out things that maybe maybe from the car itself we aren't allowed to actually do, but programmatically you could do it. So we also want more people to be able to work on one machine. As you can see, it's a bit hard for many people to work on one device on its own. So that's why we set up a way to use a Raspberry Pi and SSH inside to be able to have many people looking at what's actually happening and decide what they can get out of the reverse engineering process itself. So we also have a designated videographer. So a lot of the things that we do, we don't actually see the response directly on site on our computers itself. We will actually see it manifest on the computer, on the car itself or on the dashboard. So that's why we kind of need to do this timeline correlation in terms of the messages that come out as well as what is actually happening with the car itself. So yeah, we took the approach can be more or less boiled down to three steps. CAN dump retrieve an actual vehicle and then replay on the test bench. That's the first step. Second of all, it's about fuzzing. Once we find out, there's this bunch of CAN IDs, there are these IDs that are appearing, they seem to be doing something. We record what's taking place, and then after that, we try to reverse engineer. We try to do stuff to each of the bytes. There's only so much that we can do. We kind of brute force some of these parameters. And once we think we understand what these mean, we actually spoof these packets into a particular file and then replay it to see whether it actually has that intended effect. And then we compile our database based on all these CAN IDs, repeat the process, and ultimately we have a good understanding of actually what's happening in the communication bus on the vehicle itself. So we're going to go through a demo. These videos are there in case the demo doesn't work, like always. These things happen regularly. It's fine.
Sorry.
Okay. Alright, so what you're seeing on the screen right now is the Raspberry Pi that's connected to the test bench that we have in front over here on the Easel. So I'm going to go through some of the software that we use as open source that we use to actually do this process. So first up, we mentioned that the Cannibal itself, this CAN transceiver that we got, actually interfaces through the computer, through the Linux computer, through a network interface, and this is done over USB. So the first thing is to set it up as a device. Okay, so you will see that it actually appears here as SLCAN0 as a name that we gave to it, and it appears as a network interface, which means we can communicate over that. However, in order to set that up, it's actually on the USB. So what we did was essentially this package called CAN utils. It's spelled as CAN-utils. You can just apt-get it. CAN-utils, yes. If you apt-get it, it'll come with a suite of different kind of tools that will allow you to set this up as well as to run the thing. So the thing that the library that's used to actually, the program that's used to actually do the network interface is called SLCAND. If you press enter, you see that there's a bunch of commands. It's just simple specifying what is the baud rate, the speed, and the TTY USB that is connected to it. So we already done that for you here, so that we minimize the amount of hiccups, and we really show that it's connected. So once it's connected, you can see if you come up and you see there's actually a blue light flashing on the device itself. That's just an indicator that that there's some transmission going on because it's connected to an actual CAN bus. So how do we actually see what's happening on the CAN bus? Well, there's a few tools. So the first one is called CAN dump. So a bunch of things. It's just going to tell you that you can CAN dump what's happening on SLCAN0, which is our interface itself. And when you press enter, you'll see a whole bunch of messages. So why this is useful is because, well, at least we can log what's happening, and we can put it in a file, and we can do a grep, and we can use grep, we can do analysis to see actually what's in each of the columns inside. However, this is pretty cumbersome, and it's not really good for live testing. So what we use is something called CAN sniffer. We give the flag -C to give it some color, and we specify again SL can 0. Can 0. 0. Okay. Right, so can sniffer is more for live testing. It doesn't have the same kind of, it doesn't display all the packets that are actually happening because of the time refresh rate itself. However, whatever is highlighted in red are things that are actually actively changing in the bytes. So as mentioned before by Pei Si, you can see the can ID as well as the data fields. The IDs represent something, some function of the car that's happening, whether it's like the RPM or whether it's the door lock or something like that. And the data itself will control like what's actually happening in terms of the parameters of what's happening in that. So you have a bunch of IDs and you have a bunch of an idea of what is actually changing when nothing is happening. If we do this on a live car, what we actually see is we correlate this with the videos and we see actually what's happening. So we do a screen capture of what's happening here together with what's videoing in terms of what we're driving the car, some of the things that are happening. So, for example, I have a can dump. So if you see there's this file called can dump. That's actually the log file that we generated when we drove the car, and we actually got the dump out. So if you look a bit inside, this is what it look like. So there's just your messages inside. Once you have it in this format, we have something called can player, which means it allows you to replay all these messages that you got. So our test bench here isn't driving any car, for example. But what we can do is we can use can player, which is another part of the can utils itself. Okay, you can see that. So the help will show you that you can actually put the input file as, you can give it an input file, and what happens, okay, I should do something here first. Let me switch on can sniffer. And SL can 0. Okay, so you can see what's happening on the CAN bus, and this is what happens if I replay the thing itself. So this is simulating what's driving and all the CAN messages that are happening, right? If you look at the cluster meter, you'll see needles start to move. You'll see the speed will change. This is simulating driving when we move from parking brake, the parking all the way to drive, and other things that are happening, putting on the seatbelt and whatnot. Based on this and through like really just eyeballing quite a lot, we can try to guess, like when I do something, what is the thing that's changing over there? And this requires quite a lot of effort. So we get a few people that focus on a few of the IDs and we try to compare based on the videos what we think could be the case. Right, so this will run for quite a while, so I'm just gonna stop. Maybe we have some. Well, you can come up to see we have quite a lot of CAN dumps, so actually you'll be able to see some of the functions that will be happening. So based on that, what we then come up with is a database of all these CAN IDs. So what we do with that, all those, is that we came up with our own C program to be able to store all these things and just very automatically, I want to replay some of these messages inside the car itself. So these are specific payloads that would represent what is happening in the vehicle. So let me just show you some of these examples. So let me do a can sniffer again. And -C, SL can 0. Alright, so these are the things that are again happening in the car, nothing much. Let's go for a visual one. Okay, so there's a option 1 of our code says that demo the RPM change. So what is going to happen, RPM is the revolutions per minute. It's just going to show the needle moving from 0 to 8,000 RPM all the while, and go back to 0. And this just shows, all you see is not that whole bunch of messages, you just see one particular message that's actually coming out right now compared to when it's not doing anything. So, I mean, this is demonstrating that actually, okay, we figured out that this ID is actually responsible for this. So I think another more visual one is also the gear change. So there are many gears inside the car. Sometimes you may not be able to activate some of these things, like based on the handle itself. Sometimes it's just disabled. But through programming the CAN ID, you can actually switch all of them on. You can actually, but this at this point it's just a visual display. We've tested; it doesn't really affect the car. But there are some ways that it could lead you to do other things to the car, like of parameters that are not actually available for you to control in the car system itself. Yeah. If you're interested to find out more and play with our setup here, we have a booth over there. So this is like just it for the demo. We have a lot more to show, but this is the idea of the methodology that we go to compile the database and then ultimately design ways that we can think would be potentially dangerous and things that an attacker may want to do that would affect the driver itself. Yeah, I'm going to switch back to the slides. Yeah, so some observations of the things that we conducted based on our reverse engineering and compiling this database is that, well, it's really easy to do. Like, we did it in a month, like what Alina mentioned. Just being curious about some of the things inside. It's a broadcast network. You don't have to do any crypto verification, any authentication whatsoever. And these vehicles are on the road. So actually, if you're in the car, you're able to access through these two wires. You could probably do quite a lot of things that would mess with the minds, like a malware-infested, like adware-infested car or something. But yeah, you could probably think of creative ways of using this to actually distract the driver or make it dangerous for the driver itself. The things that we actually be able to test were the replay attacks and the spoofing. Replay attacks in terms of just dumping out a can dump itself and then replaying it. And spoofing is just for the specific IDs that we're interested in. The impact of attacks on vehicles and humans. Mentioned already, the replay attacks on vehicles can result in unwanted error codes that can break the vehicle, can make it really hard for the driver to actually control the vehicle, as well as spoofing itself, unnecessary fear in the driver when you see something that you don't understand what's happening when you're driving at a high speed. This can create unnecessary risk for the driver and the people around him. Yeah, so we already mentioned that we actually unfortunately managed to cause an engine check light to happen as well. So this is one of the dangers of kind of testing on the actual vehicle as compared on a test bench. But if you are able to control even the engine, this engine check light and what kind of message is inside, it could affect the car in ways that we wouldn't know about. Yeah, and this is some of the things that we are conducting more research on as well. Yeah.
So now we'll be talking more about our next steps. Our future plans is to continue working on this particular ECU. So there are some things that we haven't tested and are still in the midst of testing, which is the UDS command, the Unified Diagnostic Services Code. So that itself can, at low speed, can actually control the brakes of the car, can actually kill the ECU by sending ECU reset commands. We are also working on key fob attacks, which I'll show later. And recently we just purchased the immobilizer. We are trying to reprogram the vehicle identifier number or the VIN of it because we actually purchased it from different cars. So it will not work directly with this ECU. So either we reprogram the ECU or the immobilizer to actually, make the whole thing work. Right. So for the key fob attacks, because we only had the car for one day, these are the things that actually we found out. It operates on two different frequencies. So it's 433 megahertz. And we actually, because of the immobilizer that we bought, the other key that we had operates on 315 megahertz. So there are two frequencies being used for this particular car make, and it runs on PSK. So, and how we actually found out is because we use GQRX on the extreme right-hand side of the picture itself. You can see two peaks on the frequency, shown on GQRX. And we actually use RTL, SDR, Yardstick 1 and Blade RF. So the RTL, SDR is only able to receive signals. And then the Yardstick 1 acts as a jammer. As you can see on URH itself, the Universal Radio Hacker. There's a lot of noise when we execute the code and when we press the key. So, basically the car cannot receive any signals at the point of time. And we use the, URH to actually capture the unlocked signals as well. And the Blade RF to actually transmit of this because Blade RF is dual frequency. You can actually do that. So we are in the midst of planning for prototype 2 right now. We hope to be able to work on more connected vehicle functionality under the SAE level 3 to 5. And through that, we can work on adaptive cruise controls, ACC, or the advanced driver assistance systems, ADAS, that runs on CAN, which we will be able to control and modify some of the features on it. And ultimately, we want to work on autonomous vehicles and contribute towards the safety regulations of the AV industry. Right, so some key takeaways from this presentation. As we all know, cars are increasingly connected. Security by design should be implemented for all vehicles, which we actually see it now on most latest car models. Mapping out attack surface area should be identified before setting up the test bench. So this is one of the key things that we did not do, and we were running around in circles, thinking of which parameter to actually attack first. So this is actually pretty essential if you want to build your own test bench. And for future vehicles, we can actually reduce the attack surface area by performing network segregation to isolate connected components to control the automobile itself. Right. So if you're interested in car security, do come and join us. We run on a weekly meetup basis, and we actually do a lot of hands-on on our test bench itself. Right. Thank you. So too much car security, we go crazy. Unfortunately, Lucas is not here. But
No,
yeah.
he's here. He's here.
Oh, he's here. Oh, Lucas, right. So yeah, this is mapping out ECU.
Thank you.
Right.
Thank you so much. One round of applause, please, for the group. We've run out of time. So unfortunately, we don't have too much time for Q&A, but I really wanted to acknowledge at least the most upvoted questions, simply because this question has received the highest number of votes ever all day today. 12 votes. For this question from John, how to prevent this vulnerability. So if you can spend 30 seconds to answer that really quickly, because we have to go to the next speaker.
Which vulnerability? You're talking about the replay attack?
Is John here in the audience? Because you get a prize too.
Oh, okay.
Yeah.
Oh, he's right there.
Which vulnerability are you referring to?
Do you want to try to answer?
Here.
Sorry?
Spoofing. Okay, the spoofing
attack.
is okay.
Yeah. So there are a lot of, for latest car models, right? You can't actually do the replay attack for latest car models because there's a lot of encryption and different types of protection being placed on the ECU itself. So you can't actually do that on the actual vehicle for this replay attack. So, but for the purpose of this presentation, we actually use an old car so that we can actually simulate and know what we are dealing with to understand. Because we come from a black box approach, we don't know what will actually happen to the car. So this actually helps us to better understand it. But replay attack will not actually work on latest car models for some of the vehicles with this type of prevention in the ECU.
Also want to note on that, like newer vehicles may be more secure in that aspect because of the higher processing power. But the thing is, if it's on the road itself, it's not just new vehicles. And old vehicles do, even if it's just one of these old vehicles that's just on the road, it affects whoever is driving around that person itself. So there's still some merit to actually doing some of this research of cars that are still being bought and being used all over the world itself, rather than just on the newest vehicles. Yeah.
Okay.
So yeah, we want to award something to the top.
Yeah.
Yes.
So over there, maybe you
Should we
can.
like come down?
Yeah, you can come down and we
Okay,
can
so
pass
we'll
you
give
your
a few
slide.
minutes to
that
for the
run
next
over?
speaker to come, and there'll be a
Okay.
slight changeover time. Thank you very much. Another round again.